You have shipped a model that sorts the good from the bad, and for 3 weeks it looks perfect. Then you get asked the only question that matters. Why did it say no to this one? And you are guessing. You have a score. You have a threshold. But you have nothing you can point at and say, right there, that line, and here are the examples that hold it in place. Hold that question. We will come back to it in the final minute, because the answer explains something much stranger. Why is a method from the middle of the 1990s still the tool that careful people reach for when they have very little data and a decision they will be asked to justify? You already know the shape of the week that follows. Your reviewer wants a reason. Your legal team wants a reason. Your users want a reason, and what you have is a score that moved. So what do? You spend 2 days inventing justifications after the fact for a boundary you never understood. And what does that cost you? Not your accuracy. Your credibility. So let us give the thing a name and keep it for the whole episode. Warden is the small service a 2-person marketplace team runs to screen new listings. Everything that gets posted goes through Warden, and Warden says allow or review. 2 inputs to start with, chosen because you wanted something you could draw on paper, how far the asking price sits below the going rate, and how old the seller account is. Here is the explanation you have probably given in a review without examining it too closely. Warden works because it finds the best line between the honest listings and the fraudulent ones. Simple. And it sounds like it says something. But we should really avoid defining a method using a word we have not defined. What does best actually mean here? Draw 2 clouds of points on paper with a clear gap between them, and now count the straight lines you could lay in that gap. There are infinitely many. Every single one separates your data perfectly. Every single one scores full marks on the thing you were measuring. So best must mean more than separates the training data, because that property leaves you holding infinitely many answers, and a definition with infinitely many answers has told you nothing at all. Let us try again. Maybe best means the line that makes the fewest mistakes. That feels closer, and it is how most of us were taught to think about a classifier. But look at what that gives you on your own data. If your 2 clouds are cleanly apart, thousands of lines make 0 mistakes, and you are back where you started with no way to choose. And if the clouds overlap, this definition quietly instructs you to shove the boundary straight through the middle of the overlap, hugging the messiest rows in your entire dataset. Is that really the line you want to defend to a reviewer? Let us try this one more time, and let us change the question rather than the answer. Instead of asking which line is right, ask how much room a line has. Take any straight boundary you like. Push it sideways until it touches the nearest honest listing. Now push it the other way until it touches the nearest fraudulent one. That empty band you just measured is called the margin. That one change fixes everything the earlier attempts left vague. Among all the lines that separate your 2 groups, exactly one of them sits in the middle of the widest possible empty band. Not thousands of candidates. 1. The answer is unique, it is fixed by geometry rather than by taste, and you can compute it without arguing about it. Finding that band is what a support vector machine does, and the width of the band is the whole idea. Now, which of your listings actually decided where that line went? Only the ones touching the edges of the band. Take a listing that sits deep inside the honest cloud and move it around, the boundary stays exactly where it was. Delete it entirely and the boundary stays exactly where it was. The points that touch the edge of the band are called the support vectors, and they are the only rows in your dataset that the boundary knows about. Note, on Warden the fit came back with 41 support vectors out of 60,000 rows. That is the number worth sitting with. 2 features, 60,000 training rows, and the entire decision surface is pinned in place by 41 examples that you can print out, read, and hand to somebody. That is not a property of the library you used. That falls out of the definition of best you just chose. Analogy, think of 2 long rows of parked cars with a gap between them, and you have to get through. You do not aim to barely clear the mirror on your left. You aim for the middle of the widest gap, because that is the choice that survives your own imprecision. A boundary in the middle of a wide band survives wobble in your inputs for exactly the same reason. Is that argument rigorous? Only partly, and it is worth being honest about which part. There is real theory connecting a wide margin to how well a model generalizes, and it also has assumptions in it that your listings almost certainly violate. What is not hand-waving at all is the practical half. A boundary held in place by 41 edge cases moves less when your inputs are noisy than one threaded through the crowd. One more property before we break it, because it is the reason this family behaves so calmly. The problem of finding the widest band is convex. There is one optimum, and the fit either finds it or tells you it failed. No random seed, no restarts, no two engineers arguing about which run to ship. If you have ever spent whole afternoons chasing a result that would not reproduce, you know what that is worth. Warden version 1 is that line, fitted on your two inputs, and it works beautifully. For how long? 11 days. Then a seller posts a listing priced far below the going rate from a 5-year-old account with a spotless history, and it is fraudulent, and it sits deep inside the middle of your honest cloud. Look at the shape of what just happened. There is no straight line that separates your rows anymore, so the widest empty band has width 0, and the recipe you just learned has nothing at all to hand back to you. This is the point where most people quietly abandon the whole family and go looking for something more fashionable. Do not. Warden version 2 lets the band be violated, for a price. Every row that ends up on the wrong side of its own edge, or inside the band, is charged a penalty in proportion to how far in it went. The fit now balances two things against each other: keep the band wide, and keep the total penalty small. One knob sets the exchange rate between those goals, and it is the single most consequential number you will tune. Turn that knob one way and you are telling the fit, I trust these labels, follow them closely. Turn it the other way and you are saying, my labels have noise in them, prefer the wide band even if some rows fall inside it. Which of those is right for your problem? It depends on how clean your labels really are, and no amount of theory will answer it for you. You measure it. In practice, on Warden the knob was the difference between 91% and 96% agreement with a human reviewer, and the value that won was not the default. Search it across 4 or 5 orders of magnitude, not 4 or 5%. And scale your columns before you fit, every time, because the band is measured in whatever units your columns happen to arrive in, and a column counted in days will otherwise shout down a column expressed as a fraction. Then Warden meets a pattern that no line can express, however generously you price the violations. Say the fraudulent listings turn out to be a combination rather than a direction. Very new accounts are fine, very old accounts are fine, but accounts around 3 weeks old, priced slightly under market, are almost all fraudulent. Draw that on paper. The bad rows form a blob in the middle with good rows all around it. Ask yourself honestly, is there any straight line on that page that gets it right? There is not. And here is the move that usually gets taught as magic, so let us take the magic out of it first. You add a third input by hand. For every listing you compute the square of its distance from the center of the picture, and you plot that as height. The blob in the middle is now sitting on the floor and the good rows around it have risen up the walls of a bowl. In 3 dimensions a flat sheet slides straight between them. The boundary was never a line. It was a circle, and a circle is a flat cut through a bowl. So the naive fix works, and working is precisely what shows you why it will not carry you. How many columns would you need to catch every pairwise interaction among 20 features? Roughly 200. For triples, thousands. For the kind of open-ended flexibility that catches shapes you have not thought of yet, the space you would need is infinite, and you would have to write it down before you could fit anything inside it. Everything you gained in expressiveness you pay for in memory and patience. Here is where the trick lives, and it is algebra rather than magic. Write out the fitting problem for the widest band and look at the shape of it carefully. Where do your raw inputs appear? Nowhere on their own. They only ever appear inside dot products, which is to say the fit only ever asks one question about any two of your listings: how similar are these two? Every place your raw numbers could have entered, what actually enters is a single number comparing a pair. That is the entire opening. If the fit only needs similarities between pairs, you never have to build the enormous new space at all. You only need to be able to answer, for any two listings, what their similarity would have been had you built it. A function that answers exactly that question, while constructing nothing, is called a kernel. Substituting one for the other is what everybody means by the kernel trick, and now you can see there is nothing mystical in it. Two of them do most of the work in the world. The polynomial kernel returns the dot product you would have got by multiplying your features together in every combination up to some degree, which is how you get interactions without ever writing out the columns. The radial basis function kernel, which almost everybody just calls the RBF kernel, returns a similarity that falls away smoothly with distance, and it corresponds to a space with infinitely many dimensions. You are fitting a flat boundary in a space you never built and could not write down, and the price is one function call per pair of rows. Case in point, none of this is a story about theory. Vapnik and Cortez published the soft margin version in 1995 out of Bell Labs, and for most of the decade that followed, kernel machines were the strongest thing anybody had for reading handwritten digits. On NIST, a polynomial kernel machine went toe-to-toe with the best neural networks of that era. LibSVM, the library most people were actually running, came out of a university group in Taiwan and is still the engine underneath the support vector classifier in scikit-learn today, which means you have very probably called it without knowing. Now the honest part, and this is where the family stops being your answer. Fitting one of these costs somewhere between quadratic and cubic in the number of rows, because the fit reasons about pairs of rows rather than rows. At 60,000 rows that is comfortable. At 2 million rows it is your whole weekend, and the tools people genuinely reach for at that scale, XGBoost and LightGBM and anything running on a graphics card, will still require far less patience from you for a better number. Caveat: the kernel is a modeling assumption you are making, and it is not free. Choosing the RBF kernel commits you to a claim that your problem is smooth and its width parameter interacts with the penalty knob, so you are searching a grid in 2 dimensions with cross-validation rather than tuning one number. And if you skip the scaling step, the RBF kernel will hand you a boundary that is essentially noise, and it will look confident while doing it. Compare this with what the model actually hands back. A support vector machine does not naturally produce a probability. It produces a signed distance from the boundary, and converting that into something you can calibrate needs a second fitting step on data you held out. If your product needs a well-calibrated probability more than it needs a defensible boundary, that is a genuine argument for choosing something else, and you should take it seriously rather than reaching for the tool you just learned. Now back to your listing, and to the question you could not answer at the start. Warden version 3, with the RBF kernel and a penalty tune on real held out weeks, said review. And this time you can say why. You pull the support vectors nearest that listing. 9 of them sit close by, 7 fraudulent and 2 honest, every one of them from accounts between 2 and 4 weeks old priced under market. That is your answer. Not a score that moved. 9 specific historical listings that hold the boundary in place at precisely the spot where this one landed. So what changed between the model that could not explain itself and the model that could? Nothing about the data, and almost nothing about the accuracy. What changed is that you chose a definition of best that names its own evidence. A maximum margin boundary is defined by a handful of rows, so the explanation is not something you bolt on afterwards with a second library. It falls out of the geometry. And that is why a method this old refuses to die. On 400 rows, with 2 families of thing you have to tell apart and a decision somebody will ask you to justify, a boundary that hands you its own evidence is worth more than 2 points of accuracy from something you cannot interrogate. On 4 million rows, it is the wrong tool, and knowing which situation you are in is most of the skill. So before you reach for this on your next problem, ask yourself these 5 questions, in this order. How many rows do you honestly have, and can you afford to fit that reasons about pairs? Are your 2 classes really 2 classes, or have you flattened something with more structure than that? Do you need a probability, or do you need a boundary you can defend out loud? Have you scaled your columns, and are you searching the penalty and the kernel width together rather than one at a time? And the last one, which is the one people skip, if a reviewer asked you to name the rows your decision rests on, could you? Answer those 5 before you fit anything, and the fit becomes the easy part. Get them wrong and you will own a beautiful boundary you still cannot explain, which is exactly where this episode started. Whether the trade is worth making on your problem is your call, and it should be, because you are the one who has to stand behind the answer when somebody asks.